So in the previous lecture, we established conditions that guarantee uniqueness in our extension problem. So with regards to the existence of that measure, we need the concept of another measure called an outer measure. So what is an outer measure? So a function mu star defined on the power set of x to the set of non-negative extended real numbers 0 to infinity, including 0 and infinity. This function will be called an outer measure on x if it satisfies these three properties. If it is monotonic, sigma subadditive, and the outer measure of the empty set is 0. Okay. So here, the difference between a measures that we replace sigma additivity by two properties, monotonicity and sigma subadditivity. What is the advantage? Well, you know that the power set of x is always a sigma algebra on x. So the advantage of this is that mu star, the outer measure, is defined on all subsets of x. However, the disadvantage is that mu star is not additive. So, or hence sigma subadditive. Okay. So although the outer measure is defined on all subsets, one can provide examples wherein an outer measure is not necessarily additive, and in particular, it will not be sigma subadditive. So, well, an example is provided in the course notes. So if you look at the appendix, for instance, in the case of the Lebesgue outer measure, that outer measure is not additive, and that relies on the existence of non-measurable sets. And the construction of non-measurable sets are obtained from the action of choice. So if you want to see that example, please look at the appendix of the course notes. So to reiterate, the advantage of this outer measure is that it is defined on all subsets of x. However, in general, it is not additive. Okay. So this is not the measure that we are looking for in the extension problem. So if that would be the case, then what would be the main idea to obtain the measure? So here we would like to restrict the outer measure. So we consider subsets of x wherein additivity and later sigma additivity will be satisfied. Okay. So for that restriction, we consider what we call measurable sets. So let us define what do we mean by measurable sets. So a subset of x is said to be measurable, or to emphasize the outer measure, mu star measurable if I take any subset E of x. Okay. To have an idea of the definition, let us consider, let's say, a set A and a set E. So this part here is the intersection, and this part here is the difference. So this would be A intersection E, and this would be the complement of A intersection E. So we call E here as the test. Let us call this as our test set. So take a test set, say E, then this set A will be called mu star measurable if I take the outer measure of the test set. Then the outer measure should be the sum of the outer measure of these two parts, namely A intersection E and A complement intersection E. So again, a set will be measurable if you take, let's say, this test set E, and then the outer measure of this test set should be the sum of the outer measure of those elements in A, the measurable set, and the complement. And based on this definition, we will see later that this will imply additivity, and hence sigma subadditivity in the future discussion. Okay. So let us denote the set of all mu star measurable sets by sigma of mu star. This notation sigma will be clear later. So this is the collection of all subsets of A of X, wherein A is mu star measurable. Well, sometimes this is called mu star measurable in the sense of Karatidori. Okay, but for simplicity, we shall say measurability or mu star measurability. Now, if we apply the subadditivity of the outer measure, well, that is the case because it is an outer measure is sigma subadditive, and the outer measure of the empty set is 0. So you can take simply the all but a finite number of sets to be empty, then you get a subadditivity. So subadditivity of the outer measure implies the following alternative definition for measurability. So a subset A of X is measurable if and only if, okay. So in the case of subadditivity, one inequality is satisfied. In other words, less or equal. Since these two, the union is equal to E, okay. So the outer measure of the union is less or equal to the sum of the outer measures, which is, as I said, subadditivity. So by subadditivity, this inequality is always true. Hence, to establish measurability, we only need to verify one inequality, and that is the outer measure of the test set to be greater or equal to, let's say, the outer measure of the set A intersection E plus the outer measure of the set complement of A intersection E for all E, which is a subset of X. And in fact, it is enough also to verify this in the case where the set E has a finite outer measure. Because if it is infinite, then this inequality is trivially satisfied. Okay. So that's an alternative definition of measurability. We only need to prove this part here. Because as I said, subadditivity has the reverse inequality. Okay, so you might guess, due to this notation here, that if you collect all the mu star measurable sets, they form a sigma algebra on X. And that would be our next theorem. Okay, so here it is. The set of all measurable subsets with respect to the outer measure of mu star is a sigma algebra on X. So let us look at the proof. Let's start with the first step, and that is showing that this is an algebra. So first, let us verify if X is measurable. Okay, so the outer measure of E, let's say, what is E? So let us take E to be a subset of X. We can write this as mu star X intersection E, because this intersection is simply E. If we add the outer measure of the complement of X intersection E, this is the empty set. Therefore, this outer measure, by definition, is equal to 0. Okay, and according to the definition of measurability, this implies that X is indeed measurable. Okay, now how about closure under complementation? Well, the definition, as we go back to the definition here, take note that this definition is symmetric with respect to A. Okay, in other words, if I have a measurable set A, then for all subsets E of X, let's start with the definition of measurability. So mu star of E is the mu star of A intersection E plus mu star A complement E. So what will I do is swap these terms. So, and then write the complement as this one. So it's the same term. However, with respect to A, we can write that as the complement of the complement. So therefore, for any test set E, the outer measure of E is equal to the sum of the outer measures of those sets in E that are in the complement and those sets that are in the complement of the complement, which is A. So by definition, measurability, this implies that the complement is also measurable. So for this step, it now remains to show that sigma of mu star is closed under finite unions. So for that, let us start with two sets, two measurable sets, say A and B. Okay. Then you take a subset A E of X. Okay. Let's start with measurability of A. So mu star of E is equal to mu star of A intersection E plus mu star of A complement intersection E. Okay, now to have a visualization of this one, let us consider three sets. So let's say this is A, this down here is B, and you have a test set, say E. Okay, so let us look at A intersection E. That would be this set. And if we look at, okay, before proceeding, how about A complement uh, intersection E? That would be this part. Okay, now let us use A complement E as, or A, how should I say this? Let us look at A complement E as the test set for B. So let us look at this part here and use this as the test set for B. So this would be your test set for B. Since B is measurable, I can replace this by what? Mu star B intersection A complement intersection E plus mu star B complement intersection A complement intersection E. So that would be the second term, and the first term will be retained as is. Okay, so let us move this to the right. Let us investigate the second term, or the third term. So this one is equal to, by De Morgan's law, A union B complement intersection E. And how about the second part? So if we look at this set, B intersection A complement E, that would be this part. So that region here is B intersection A complement intersection E. And if we take this with the union of A intersection E, you can notice that here that the union of these two, so union is, so if you take the union of A and B and take the intersection of that with E, that would be the union of the green, or I should say the blue and then the red parts. Okay. So if that would be the case, then by subadditivity of mu star, let us put that here, mu star subadditive. So the sum of the outer measures of the two sets is greater or equal to the outer measure of the union. And as we said, the union is A union B intersection E. And the last term is the outer measure of the complement of the union intersection E. So looking back at this inequality, so the outer measure of E is greater or equal to the outer measure of those in the union and those in the complement. And going back to this remark here, okay, this is the inequality that we would like to establish. This is enough to establish measurability of the set A union B. Okay, so with this, we now conclude that the union is also measurable. So to summarize, so the first one, we have established that X is measurable. The second one, we have established that it is closed under complementation. And finally, it is closed under finite unions. Therefore, the collection of measurable sets with respect to the outer measure, mu, forms an algebra. Okay, so let's go to the second step. So for the second step, we would like to establish that the set of the collection of measurable sets is a Dinkin system. Okay. And how does this imply that sigma of mu star is indeed a sigma algebra? Take note that from step 1, this is closed under finite intersections. And why is that? Because an algebra is closed under intersections. And in this case, okay, this would imply that if sigma of mu star is a Dinkin system, hence sigma of mu star. Okay, so let us change the color. Hence, sigma of mu star is a sigma algebra. So recall in the previous lectures that a Dinkin system that is closed under intersections forms a sigma algebra, or is a sigma algebra. Okay, so to establish that it is indeed a Dinkin system, we only need to show that it is closed under pairwise disjoint countable union. Because here, take note that we already established that X is measurable and it is closed under countable or closed under complementation. So to do that, let's start with a pairwise disjoint collection of measurable sets, say A sub n. Okay, and let us denote the union by A. So let us take the partial union. In other words, B sub n would be the union of the A sub k's k from 1 to n. Now, take note that since this collection is a sigma algebra, so the finite union of measurable sets is also measurable. And Bn would be a subset of A for any n, because A is the union of all the terms in the sequence. Okay, so for this, let us look at the following. Since Bn is measurable, then if I take any subset E of X, the outer measure E is equal to the outer measure of those elements in E that are in the measurable set B sub n and those that are not in Bn. So here we just applied the definition of measurability of B sub n. Okay. Now we wish to look or investigate this outer measure here. So to visualize, let us consider an illustration. So let us take, let's say, n to be 3 as an illustration. Just to gain an idea or intuition of what will be the succeeding parts of the proof. So n equals 3 means that I have 3 sets, pairwise disjoint A1, A2, and A3. So let us put the labels here. So A1, A2, and A3. And let's say I have another set, let's say E. And without loss of generality, let us say that it will intersect all of these 3 sets. So this is the set E. Now, what would be the set B sub 3? B sub 3 will be divided into 3 parts, and that is A1, A2, and A3. So recall that again, B3 by definition is A1 union A2 union A3. Now, let us look at A3 or B3 intersection E. So let us look at, let's say, A3 intersection E. That region would be this part. And you can observe that this is the same as A3 intersection B3 intersection E. Okay. Since we are, the sets are pairwise disjoint, so A3 intersection B3, take note here that this is the same as B3. or I should say A3. And that's the red region there. Next, let us look at the complement. How about A3 complement intersection B3 intersection E? You can notice that this is simply B2 intersection E, because this part is equal to B2. So if you look at the complement of A3, so this would be, and then take those elements that are also in E. So that would be this part. So this is what? A3 complement intersection E. And if you take the intersection of that with B sub 3, in other words, taking the intersection with these blue parts here, this one, and this one, you end up with the original green parts. Hence, that would be this part here. Okay, so what is the significance of this example here? If we take, for instance, take note that by definition, before we proceed, is basically A1 union A2. So that's B2. So the significance of this is that if you look at these two terms here, you end up with, let's say, B2 intersection E in the second case, and A3 intersection E in the first case. Okay, so, well, proceeding with that, it is plausible, okay, to claim that the outer measure of, let's say, Bn intersection E, okay, that would be, in this case, the green and then the union, is the sum of the outer measures of AK intersection E, K from 1 to N. Okay, so if you view this equation, it seems that mu star is somewhat, at least in this example, additive, because Bn intersection E would be the green and then the red parts. So if you want to take the outer measure of those, then we just take the outer measure of the constituents or the components. Okay, and the proof of this will be established via induction. Okay, so let's start with the proof of the claim. So in this case, let us do this by induction on the number of elements, or the index n. The basis step is clear because, so the claim is true for n equals 1, since A1 is the same as B1. Okay, so let us put this down and copy our claim. So let us copy this on the next portion. And that's the claim. So if n is equal to 1, then in this case, the left-hand side would be simply as B1 intersection E, and the left-hand side, the only set that we consider is A1 intersection E. So the sum is simply a one term. So this, since A1 is equal to B1, then the two coincide. Okay, so basis step is trivial. Let us now go to the induction step. Okay, so in this case, suppose the true is claim, the claim is true. So, for n minus 1 sets, this is our induction hypothesis. We wish to show that it is also true for n sets. Now, let's start with the fact that an, by assumption, is measurable. So let us take bn intersection E as our test set for a sub n. So if this is our test set, the outer measure of the test set should be equal to the outer measure of the following. So you divide the set into two parts. In other words, you divide Bn intersection E into two parts. The first one is in A, and the other one in the complement. Okay, by induction, one can show that this is equal to An intersection E. So going back to the figure in the previous discussion, so this is, well, in the case where n is equal to 3, this part here, you end up with simply A3 intersection E. In fact, you could show this by the definition of B3. And on the other hand, with respect to the complement, we get B2 intersection E. That is the previous set B sub 2. So applying the definition of Bn, one can also show that this is B2 or B sub n minus 1 intersection E. Using these representations, we now have the outer measure of An intersection E plus the outer measure of Bn minus 1 intersection E. The second term, so we take the first term as is. The second term would be applying the induction hypothesis. So since our claim is true for n sets or n minus 1, then this should be the sum of the outer measure of A sub k intersection E k from 1 up to n minus 1. And you can write this simply as the sum k from 1 to n. This will do the last, or this is the last term in the sum. And we have this. Okay, so this is the induction, or yeah, this is the induction step. Hence, this approves the claim. So going back to what we have discussed previously. So this part here. So let us copy that one and paste it here. There are missing parts. So the outer measure E is equal to the outer measure Bn intersection E plus the outer measure of Bn complement intersection of E. Now using our claim, this one is equal to the sum of the outer measure of A sub k intersection E plus the second term. So k here from 1 to n. Okay, so let us retain this first term at the moment. And take note that by construction, Bn is a subset of the union, which is A. So by De Morgan's, or by taking the complement, so the complement of A is smaller now with respect to the complement of B. Therefore, the outer measure of Bn intersection C compared to the outer measure of A complement intersection E, that would be larger because Bn complement is larger than A complement. So based on this inequality, we can now pass n to infinity, and this would now turn to an infinite series. So with that, we will get that the outer measure of E is greater than or equal to this series. So this is the sum of the outer measure of A n intersection E, or I should say K, K from 1 to infinity plus the outer measure of A complement intersection E. And here, let us apply the outer, or the sigma subadditivity of the outer measure. So the sum of the outer measure is greater or equal to the outer measure of the union. So that is for the first term. The second term is as is. Take note that by definition, this is A, and you can see immediately from this inequality that A, which is the union of the A sub case, is measurable. Here we only showed one inequality. As we said, this is enough according to the subadditivity or subadditivity of the outer measure. Okay. So to summarize, we have verified that if you have a pairwise disjoint collection of elements that are measurable, the union is also measurable. And going back to the goal of the second step, okay, this will imply that the set of measurable sets forms a Dynkin system. And since this Dynkin system is closed under intersections, it is also a sigma algebra. Okay, so now we have verified that the collection of measurable sets forms a sigma algebra on X. So how can I utilize this to form a measure? Well, in fact, the construction is easy. We only need to restrict the outer measure to the set of or to the collection of measurable sets, and then you will obtain a measure already. And that is the content of the next theorem. So this is the Karaty-Dori theorem for outer measures. If mu star, let's say, is an outer measure, then if we consider the restriction of the outer measure to the measurable sets, which we know from the previous theorem that it is a sigma algebra, then this is a measure. So from an outer measure, how do we create a measure? So the idea is basically restrict the outer measure to the collection of measurable sets. Okay, so for the proof, let us establish two things. First, what is the value of this set, the empty set? Okay, since empty is measurable, and why is that? Because it is a sigma algebra. Okay. So in this case, this is basically the outer measure of the empty set. Hence, this is 0 by the definition of the outer measure. So that's the first criterion. Next, suppose you consider a pairwise disjoint union of measurable sets A sub k. Now, reviewing our proof a while ago, if we take E to be the union, in, let's say, going back with the proof, let us consider, for instance, this inequality here. Let us call this star. If you take E in this inequality, okay, so let us copy that for reference. So we have this inequality in star. So let us repeat that. So E is the union. So this is now the union, k from 1 to infinity, E sub k. This is greater or equal to, okay, so let us just copy the second term. So this is AK intersection E plus the outer measure of the complement of A intersection E. Okay. Of course, according to our previous construction, this is also equal to A. So the union of A sub k is equal to A. So E in this case is equal to A. So let us replace that one by A. So with this, you can see that the second term is 0 because the set is empty. And since A sub k is a subset of the union A, the intersection will be the smaller set. And from here, we see now that the outer measure of the union is greater or equal to the outer measure of the sum. Okay. Now for the other inequality, you just apply the sigma subadditivity of your outer measure. Hence, we conclude now that the outer measure of the union, the A sub k from 1 to infinity, is equal to the sum of the outer measures. Okay. Now, by assumption, A sub k is measurable. So this means that this equation here is the same as mu star restriction to sigma of mu star A sub k by the definition of the restriction of a function, as long as the argument is in the domain. Okay. So this is also measurable since the collection of measurable sets is a sigma algebra. Okay. And this left-hand side will be the same as the outer measure restricted to sigma of mu star of the union. Okay, hence these two are the same. And let us write that down. So the restriction measure, or the restriction of the outer measure of the pairwise disjoint union is equal to the sum of the restriction of the outer measure applied to the components of the union, A sub k. And that establishes the sigma additivity of the restriction of the outer measure to the measurable sets. Okay, so that is how to obtain. So how can we obtain a measure from an outer measure? We just need to restrict the domain of the outer measure to the collection of measurable sets. Before we proceed, I just want to point out here that if the outer measure of a set is 0, then that set must be measurable. So sometimes This set is called a null set. So with this terminology, take note that a null set is not necessarily empty. Okay, so we're just saying that if the outer measure of that set is 0, then we call that a null set. And this remark tells us that all null sets are measurable. Well, to prove this, it is enough to know that, okay, so A is larger than A intersection E. So what is E? So E is any subset of X. So A intersection E is smaller than E. So taking the outer measure, the outer measure of E would be larger than the intersection. And that is basically monotonicity. Now, let us look at what? Or I should say, let us apply that argument instead with A complement intersection E. Okay. So instead of A, let us use the complement. Now, if we look at mu star A intersection E, the one that we said a while ago, this is 0. Why is that? If we look at the fact that this is a subset of A, same reasoning, the outer measure of this intersection is less or equal to the outer measure of A. Now this is 0, and outer measure is non-negative. Therefore, the outer measure of A intersection E is equal to 0. So in other words, all subsets of a null set are also null sets. And based on this inequality here, okay, and take note that according to our discussion a while ago, this inequality is enough to say that A is indeed measurable. Okay, so all null sets are measurable. So going back to Caratidorus' theorem, so if we have an outer measure, we can generate a measure. And if we look, let's say, at our extension problem at the beginning of this lecture, we should start with, so starting from a pre-measure, okay, if it is possible to create an outer measure from this pre-measure, then by applying Caratidorus' theorem, we can generate a measure. So the next task that we would like to do is how can we obtain, or how can we generate an outer measure from a pre-measure? And that would be the topic for the next lecture.